Thank you very much for this occasion. Particularly, I'd like to express my sincere thanks to Professor Pollack. I knew him more than 15 years, I think. It's a long history we have. And I used to be involved in the hydrogel, but these 10 years, I shifted to non-hydrophilic systems. So my talks are different, seem to be different from that you are talking on this conference. But the other, Professor Pollack advised me to concentrate on this topic. So initially, I put this the title, what I'd like to mention about this. First portion, I'd like to express about dielectric polymer gels as an electrical active soft actuator. And the latter portion, I'd like to show some new data around the electro-optical function, in which the light deflection can be induced by electric field in the polymer gel. Now, let me introduce a little bit. This is Japan, and I came from here, Nagano Prefecture. It's a highland area, and where I live is about 450 meters above sea level. And we have active volcano around my city. It's a very good place, just like here. This place is very nice. And I live here, northeast part of the Nagano Prefecture. Now, let me get into the topic. Polymer gels have been considered to be efficient actuator. From this point, huge volume change, swelling and diswelling can induce huge volume change. That can be applied for actuator. And that's the idea initially. And another viewpoint, this is very slow, but practical application is usually difficult. But in the case of polyelectrolyte gels, which contains some amount of water, but can be actuated at very low voltage, for instance, that 2 volts and 3 volts around is enough for usually. But at the high voltage, the electrolysis occurs on the electrode, and that is inconvenient. And usually, the presence of water is inevitable. That also be inconvenient. And particularly, the large current is observed, and energy dissipation is huge. So for practical application, this has also some difficulties. That's the point I changed my viewpoint to dielectric polymer gels. But at that point, people advised me it's not adequate because the electric materials cannot respond to the electric field, DC electric field. But I tried, and it turned out to be very active, and a huge deformation can be induced in this case. That's the starting point I involved this dielectric polymer gels. No volume change is necessary, and durability is much higher than hydrogels. So that's the point. And we found most conventional polymer materials. After this, we found most conventional polymers can be applied for electrical actuators. For instance, polyethylene terephthalate, nylon, and many other polymers can be used electrically active polymer actuators. Many people don't know about that, and some technique is necessary for utilizing those actuators. The polymer gels are ranging from highly swollen polymer gels, dielectric, and the plus-size polymer gels, elastomers, and crystalline polymers, so on, have been investigated. Now, some of the plus-size dielectric polymers can show the huge strain, such as hundreds of %, and can restore the original shape when the electric field is off. Some physicists pointed out such kind of huge strain is difficult to explain, can be restored. It's impossible usually to restore its original state, but it is, and that's another issue remained. Most of the features of plus-size PVC, this is the case of polyvinyl chloride. Most of you know polyvinyl chloride has been used conventionally widely and has been believed to be inactive to the electric field. But it is electrically active And the reason turned out recently, actually we found the phenomena 10 years ago, but I couldn't believe the phenomena. So I tried many experiments and using many students. And the colossal dielectric constant was found in the low frequency range. That is very important for PVC. That's the origin of the huge strain generation by the DC electric field. These materials can also possess electro-optical functions or the piezoelectric functions too. And I'd like to introduce this kind of phenomenon later. First, what kind of strain can be used for chloride gel? This is the anode surface. This is a gel, transparent gel. And when we turn on the field, the gel leads out onto the anode surface. This is a strain induced on the very edge of the anode edge, only the anode surface. Cathode surface didn't show any change. So this is very peculiar information. And this is the illustration of the ferrite. We call this amoeba-like pseudopolymer and electro-optic grid deformation. So far, PVC is the most successful material for this kind of deformation. But to utilize those kind of deformation for practical use, I use this kind of electrode alignment. This is the cathode, and here is the gel. Then we apply electric field. This kind of deformation, gel creep out into the anode surface. And when we employ this kind of alignment, the gel bends in this way. The charge accumulation in this cathode surface, gel creep out onto the other surface of the electrode. That is this kind of deformation. And also, this deformation can be seriously affected by cluster. When we employ totally, then that kind of deformation occurs. But when we employ agitated, linear cluster, it's more efficiently induced the deformation. When we introduce this deformation, the thickness is 200 micrometers, and applied voltage is a couple of hundred volts, still high. To reduce the voltage, we can use unelectric. But as it can be expected, unelectric can permit current flow. So the energy dissipation, heat generation is huge, not convenient for practical application. Though the application voltage can go around. This is the mechanism of what kind of process is bending deformation. Accumulated charge on the anode surface can bend the gel creep out to the other surface, and the recursion charge can extend the contact area. That's the and for practical application, this is an example. Top view of the lens. This is side view of the lens. And we apply electric field. They default in this way. So actually, we can expect focus control is possible using this like this in this way. So this is a kind of very magnetic deformation can also be used in particular, and it can be used for lens. That kind of deformation can also be applied for contractile actuator. This is the cathode, this is anode. Then applied field, the creep out to the anode surface causes this kind of contractile deformation. By integrating the layer, large deformation, it can be used in this way. And some other companies try to utilize this kind of system for exchange their actuator into this type one. And if they can use this material as solenoid coil, current leak is nanoampere, actually electrical. So under very low current, large deformation, very quick deformation can be used. So they are seeking the opportunity to utilize this. Durability is the problem. Summarizing the PVC gel deformation, this is the quick deformation. Flooring deformation can also be used. And this is the gripper motion. Very swift gripper motion can be very simple mechanism, only electrode, this is nothing else. This is the gripper, very tiny gripper finger to manipulate the transfer. This is also shows strong touching force or adhesive force to another surface. 1 square centimeter can hold 2 kilograms. So it's really efficient. So this kind of thing can be occurred in this kind of system. This gripper can work over 200,000 times continuously. The mechanism is proposed this way. PMMA, this is not active solid field. And this is anode, this is just a membrane. There is no charge accumulation observed. But in the case of transfer PVC, on anode surface, large amount of negative charge accumulation was observed. On cathode, nothing happens. There is large difference, asymmetry in the charge accumulation causes that kind of deformation and that kind of activation in this case. And the reason is shown in this way. When we carry out some kind of a frequency analysis, and then this is polymer, this is plastic. By mixing them, the two components don't show any large constant. Dependency to the frequency is very low. But when we mix these two compounds and then make the gel, totally total change. The huge increase of dielectric constant is observed. So summarizing, all this high strong gel to crystalline polymer, this we visit all of these can be achieved. But plastic one is a very peculiar one, which has colossal dielectric constant with large power. So this large dielectric constant can be some other function. One of the other functions is electro-optical function. The reason why I ask my student to carry out experiments is very simple. Actually, refractive index is proportional to the square and root of the epsilon dielectric constant. So this is very basic idea. And when we check the difference, it is said in this way. Delta n is proportional to the square to the electric field or square of electric field. This term is called Popper's effect. This term is called power effect. Usually, when the medium is very homogeneous, only this phenomenon goes out, and this effect is usually very small. And in organic materials, nitrogen have been known to be a good perfect solid. But this experiment, and this is the result. When we change the cluster, all of them can show the huge increase of the dielectric constant in low frequency length, not high frequency length. So when we can allow the very slow reaction, then this will be enough. These are the things. No components show small, but plus side PVC show huge dielectric constant. And the reasoning is a cooperative phenomenon. This is a cooperative phenomenon. Polymer plus side interaction causes this kind of special function. And this is the image of the polymer. In the case of alkane, the linear cluster attached to the polymer has a tendency to extend polymer chain. But benzene type styrene cluster can lead to some kind of aggregate formation on the chain. That's the difference of a physical property. So aggregate gel can be elongated over 800%. But in this case, only 150% elongation, gel easily broken down. The physical property is totally different depending on the cluster. This is usually employed electro-optical function measurement. And this is the data. When we apply electric field to the gel, and deformation and large diffraction is observed in this case, like this. Very efficiently, light beam was shifted to in this case, to the cathode side. And this is the visual image, when we apply electric field, they can see on the surface some distortion of image can be induced. So this is the thing that we can induce by applying electric field to the gel. The phenomenon is not that simple. When we apply electric field to the cathode side and the center and anode side, the deflection is different, like this, suggesting that the diffraction index gradient in the gel is not proportional to the electric field. So some kind of ambiguity, asymmetric feature in the diffraction index exists in the gel. This is the feature. When we draw it additive and the physical and synthetic, these are the clusters. And then in the applied field, turning on every time on and off, we can see some kind of diffraction of light. This is the most difficult. And this is the cathode side. This is center. This is anode side. As I said in the previous slides, actuator function has been observed on anode side only. And the cathode side, nothing happened. But from the viewpoint on the electro-optical function, that's observed very efficiently on cathode side, not anode side. Some structural instability exists on anode side. So totally different. This is the case of additive system. Material additive, and material additive change the molecular size from large one to small one. And this is the same, the structure is very different. But as you see here, depends on the class of the structure. Material additive, which is most flexible, has shown the very highest, largest diffraction of light. The influence of the content of cluster is shown here. When we change the content from 1 to 4 in a weight ratio, PVC to cluster, then I change it this way. And at a certain position, in this case, for example, green, 1 to 6, or the maximum diffraction is observed. So depends on the cluster. The small one and the larger one, too large, is not effective for diffraction. This is the image. Actually, the laser beam doesn't go through straight. It's actually bent in the gel. But for simplicity, we measure it this way. And the result is like this. And as you see here, this is electric field, proportional to the square of the electric field. The Carr effect is observed. When the length of the electrode is increased, then the diffraction angle naturally increases proportionally. These are the phenomena that we observe. And this is a check. How the cluster behave to the electric field. And this is the molecular analog of PVC. This is chrome we use as solvent. And we check deformation. It doesn't you can't see any diffraction of the light. Just a little fluctuation is observed on the electrode. So only gel can induce that sort of large deformation, diffraction. This is a case of nitrogen, which has been known very efficient perfect solvent. And this is the case, perfect. Compared to the gel, it's very much smaller than nitrogen, very small. And actually, this is a video image. You can see some fluctuation or spot. And you can see it's very difficult to see big change of the distortion of the image. So the diffraction is small. This is the case of the PVC gel, PVC transparent gel. And when we, as shown here, as shown in the other slides, at the certain position of the polymer to plastic amplified maximum in this system. So it's just again suggesting that the larger the dielectric constant, the larger the diffraction angle. This is the same way. Diffraction angle is the function of epsilon prime. And plus control the function through additive structure information. What are structure formed in gel is not clear at this moment. That sort of phenomena can only be observed in PVA or other particles. PVA gel, we investigated on this gel more than 15 years ago, and it showed very efficient deformation. The reason why we don't use this gel for practical application is the solvent leak is inevitable in this gel. That's it, and also confirm that a lot of PVA is hydrophilic polymer, and we use the DIMSO solvent. DIMSO also be easily contaminated with water and other contaminants environment. So the producibility is not that good. So that's the reason why we didn't use this gel for actuator. It can be used. It shows very efficient deformation. But from the viewpoint of electro-optical function, it might have something. This is gel, PVA gel, long time ago, we carried out this kind of experiment. It deforms very efficiently. This is another example. There is very strict deformation can be used. Within 40 milliseconds, 90 degree bending can be used. This thickness is, I think, a very thin one, but it works very efficiently. The mechanism is simple. A charge injection from, in this case, anode, can lead to that kind of function. But we employ that kind of gel for electro-optical function. This is the case. Very clear and clean diffraction is very good performance ratio. In this case, we can use this material for very long time because we prepare the gel in the dry vessel. These are the results of diffraction angle, depending on the polymer size and polymer size. And some polymer size is that too large is not good. But in this case, 500 shows very nice response. Smaller one, I think to be very nice in this case. And the reason is a little different. This is a PVA. PVA didn't show any frequency dependence on dielectric constant. But NMP, which shows this kind of dependence. So in the case of PVC gel, the process didn't show any dependence on frequency, but NMP is different. So polymer gel structure is different. NMP leads the increase of the dielectric constant. So that's how, but addition of PVA enhance the dielectric constant anyway. So that leads to more very efficient deformation in this case. And dependence on the electric field is shown here. It's very attractive, but more likely in this case, linear, suggesting that this gel shows populus effect. And the way we summarize the data, this is PVC, this is PVA. This is almost straight line, but this is the square of the electric field. So this is the phenomenon is different. So the polymer gel is generally the same, but the structure of the gel is totally different from between these two. And from the viewpoint of the optical function, this material will be better because the diffraction is not that big, but PVA shows very efficient. But durability one, this is much better. So it depends on the use, what kind of field we are seeking is important. And this, the other case, diamond sulfoxide can be used if we employ a solvent. The very high frequency range, we can use very large dielectric constant, around 1,000, very high. So in this field, in this sense, we can use DIMSO gel also. But so far, it doesn't work well. Impurity is large amount. It's not complete for practical use. So, by summarizing my talk, the curve effect and Doppler's effect is observed because of the closer dielectric constant induced in polymer gel between the interaction from the interaction between polymer chain and plastic. And interaction between polymer chain and plastic depends on the structure of the polymer cell, of course, and plastic when changed from to solid, the totally different progress, big difference. I came from, as I said, I came from higher level. This is active volcano. This is very nice place. If we have getting, let's visit, please visit us. Thank you very much.